Hello community! Emergent phase transition in context learning. This is now part 2. Remember in my last video we looked here how to override knowledge in an LLM with in-context learning, and now I want to give you the result of today's video. So the study here by Harvard University about in-context learning of representation showed us, and I quote Harvard, an intriguing breakpoint that is reminiscent of a second-order phase transition. And Harvard found that this behavior is extremely robust across the graphs of different sizes and shows here an explicit power law scaling trend with an increasing graph size. So we work here with a transformer architecture. We explore different graph sizes and we look for the perfect learning. When is ICL the most efficient learning and training procedure for your LLM? Now, in my first video, I showed you if we have an LLM and we want to override the knowledge, it is not that we just touch on the node or on some edges. We have to maybe override here complete subgraphs, sub-networks here in our knowledge presentation if we make this simplified visualization here of our deep neural network connectome. So let's start. As we said, Harvard, increasing the amount of context leads to a sudden reorganization of the transformer internal representation in accordance here with the graph connectivity. And I showed you last time here that suggests that LLMs can manipulate their internal representation in order to reflect their concept semantics that were specified entirely in context learning. Great. So if we accept that LLMs can reorganize here the concept representation here, then we aim now how to study this behavior. We need a mathematical model. We want to understand how is the context. If we have a scaling, so is there a continuous monotonic improvement toward the context specified structure as context is added? And it turns out no. Now you please refer here, maybe you enjoy this study. If you want to go to the edge of knowledge, if you want to go to the fringe here in AI research, and please know this is research. This is not just you can copy a code and this is it. This is really research with a lot of some deep thinking involved. But if you enjoy this, this is the paper for you. And I've showed you here in my last video yesterday that if we accept that the representations are not just the token embeddings, but they are evolving here dynamically with contextual activation vectors within the LLM's residual stream of each single layer, then we understood that the self-attention mechanism is here the main driver, and you know this. But now let's look at this and let's frame this ICL representation learning now from a different point of view, because we want to build an internal understanding of it. And whenever we want to build an understanding of how a system is learning, we want to model the system. We want to build a mathematical prediction model to understand if it is really working. And here we go now. Now, Harvard is telling us, hey, we tried an energy minimization process and this seems to work fine. So let's follow this. Yeah, in my simple terms is, hey, how to model this process mathematically. Now, we have here, and this is really, we look back, I don't know, 200 years plus to Peter Gustav Dirichlet, and he was a German mathematician, and he did something beautiful. Also, he was looking here for a particular problem, which involves finding a harmonic function given here specific boundary condition. Interestingly, look at this. This is 200 years back, and we use it today in the latest AI research to try to understand new mathematical models. And he was applying this here to electrostatic fields. This is the field that we apply now, and it's amazing. Yeah? Was that electrostatic potential is described by on a boundary of a region. It extends to a potential in the interior that is harmonic when the condition, the electric field, is in a stable equilibrium. Now, this electrostatic field configuration corresponds now to a state of the system of a minimal Dirichlet energy. So we take this idea, this 200-year-old idea, and we apply it to the latest research Harvard University on AI. I am always fascinating to learn this. Yeah. He himself was not so perfect, but it took here some years. Then David Hilbert provided here real justification here under certain assumptions. He showed, yeah, that this is valid and therefore we can use it today. If we want to learn a little bit before we jump here into the explanation by Harvard, I would recommend to you here, if you want to look investigate a little bit the smooth vector field design, especially if you look here at a simple discretization of the vector Dirichlet energy. This is my go-to publication that I highly recommend. It is from 2020, and they introduce here exactly this corresponding vector Dirichlet energy function here, where U is here a smooth vector valued function on omega, and they're working here with a specific Frobenius norm. So if you want to have an idea what we are talking, this is the paper for you. They go here and they explain in chapter 2 the theoretical background. So if you're really into mathematics and you say, hey, I really want to understand this on a deep level, I would highly recommend here, especially 2.2 here, where they show you how easy it is to derive here the mathematical equation of the vector Dirichlet energy function. This is what we are going to work with. This is what we are going to calculate with. And yes, it has a beautiful, rich history in mathematics and theoretical physics, and now we apply it in AI. Now, just to make sure, this vector Dirichlet energy that is just defined here quantifies now the smoothness of a vector field. And this is what we are talking about, no? Just like the scalar did, yeah, for the scalar function. And now this makes the vector Dirichlet energy and its associated Laplace equation useful for the applications requiring here a notion of a vector field smoothness. So this is what we want to experiment now with. The smoothest or the smoothness of a vector field is here given by certain constraints. Beautiful. Just give you this example. Imagine you want to fit a smooth vector field to the red vectors. You can see we have here 1, 2, 3 red vectors, and now you have to build or fitting here a smooth vector field here to the vectors here, and they give you here all the mathematical details I do not understand in detail for this particular topic, but we are just luckily just looking here at the AI implementation. If you wanted here an extreme simple idea, this is just a feeling I can give you here. Imagine we have this network. Imagine we have here a complexity, a high dimension, n-dimensional complexity. And now we want to override knowledge. And this is the LLM that is shipped by Meta or whatever. And now we want to have in-context learning, and we want to activate in-context learning. And we are aware there is maybe a discontinuity here for this. So therefore, what we want, in a simple picture, we want to extract here a subnetwork, and we want to substitute this subnetwork with the in-context learning inside, with the in-context learning examples, with the examples given here in the in-context learning here, the few short examples. But they have to have here a smooth vector field that fits into the greater vector field representation. And everything should be smooth and beautiful, and everything should have here a beautiful continuity. There should be no spikes or no empty region where you have no connectivity. So if you go for the real simplest, I would go with this one. Yeah, if you want to go a little bit more complicated, I try with this simplification. This is just me somehow trying to make this understandable if you encounter this the first time. So we want to find here a smooth vector field, given that we have certain boundary conditions. Remember the electrostatic field by Dirichlet? This is it. So we need to find now a mathematical function that exactly describes this behavior, and we have Dirichlet. So we want now to find a smooth solution in our, if you want, complex n-dimensional knowledge manifold. And it turns out this smooth solution is a minimizer of the vector Dirichlet energy. If you want to see this in further details, as I told you, great. But luckily, Harvard in its paper also kind of simplified this here to this representation. So if you just want to focus here on the Dirichlet energy, equation 1, 2, and 3 of the Harvard publication is here a simple entry into this topic. So Harvard now tells us, okay, great. So the measures above indicate whether the neighboring tokens, our node in our graph, and the ground truth graph have a similar distance or have a small distance between the representations. Thus, as the model now, our learned ICL model now correctly infers the correct underlying structure, what we want to see in our mathematical model is now a decrease in the Dirichlet energy, as I showed you. So we have now a beautiful model, and we can see, does it work? Does it fit? And Harvard calculated this now. And here you have it beautifully. So let's start. On the x-axis, we have the contact length of our LLM. And here Harvard calculated 4, and this is here a Llama 3 LLM, and normalized Dirichlet energy. Yes, we have normalization factors, but this would be too much detail. Just look at what happened. So we have here in blue a mid layer, layer number 18, and then here in whatever pink, a layer 30, so one of the last layers here. And then in green, we have here the accuracy. So if you look at accuracy, just look at accuracy, we start here somewhere at, I don't know, 20%, 40%. We are relatively stable if we increase the context length, but then at a certain point, the context length starts to go up. So we have here, if you want here a breakpoint, we have here stable, and then we have kind of a linear. This is here for the grid configuration I showed you in video number 1 yesterday. If we go to the ring topology of our data representation that we want to find, same structure, accuracy, normalized Dirichlet energy, you see, just look at here, the green, the accuracy from 0% to 100% of our system. You see, there's here an extreme jump here to 100%, and then more or less we are stable close to 100% accuracy. This is exactly what we want to reach in our model. We don't want to have to stop with the ICL in the RAG system, the augmentation part here, somewhere here with this context length on examples that we provide. But we want to have here, of course, the best accuracy that we can get. Isn't this interesting? And now, as you see there, this region that are really here where you transfer here from a real low performance of 20%, and when you come out here, you're above 80%. So this region here is one of the most interesting regions if you want to understand this, if you want to model this. And Howard tells us, hey, this leads us to the claim that as the amount of context is scaled, there's an emergent reorganization of the internal LLM representation that allows the model to perform well on our in-context graph tracing task I showed you in video 1. So there you have it. There is something absolutely fascinating happening, and if the theory of Harvard is right, we can describe this system behavior with a mathematical model that is based here on the minimization of the Dirichlet energy of the system. And they say, building on the results from previous section here, Howard tells us we now put forward a new hypothesis for why we are able to identify such structured representation from a model. I showed you the ring, the hexagon, or maybe the grid representation in the last video. And Howard tells us, we now say that the model internally runs our LLM with the in-context learning, internally runs here an energy minimization process in search of the correct structural representation of the data. And this is mind-blowing. Just to be sure, no? When we talk about energy, this is not the electricity, the energy that the compute cluster uses. No? This is here a very graph-specific mathematical expression of the Dirichlet energy. So this is an abstractum that we've chosen in a particular representation. But if we do this, if we see this as a minimization problem, then interestingly, the LLM builds here in its internal representation, remember here PCA, the correct structural representation of the data set. Therefore, we are now left with the main question here. Yeah, of course, this does not come here suddenly, because if you look back here at the beginning of 2023, you had this study here, the transformer from an optimization process, and they looked here into also, is it possible to have an association between an energy function minimization and the deeper layer of self-attention? So for years, there was this idea, can we describe this in a mathematical model? But of course, there's one paper, this is the Bible if you want. This is from Yale University, Spectral and Algebraic Graph Theory. Now, if you read Incomplete 2019, you see it's an old paper, forget it. This 400 pages. If you want to know anything about spectral algebraic graph theory, here you'll find it. So maybe you have a look at this. This here is the link. So whatever I ever had open question, this was the paper to read. And if we take this now, and especially may I put your attention here a little bit to the spectral part here. The spectral embeddings now often used to draw here a graph on a plane on a two-dimensional manifold, and in many cases it will preserve here the structure of the graph. Look here at the publication, we see here exactly here the spectral embedding, and we have here the ring graph, and here we have here the grid graph from video 1. But please notice, this is not the embedding that you know from the transformer. This is not an internal representation here given here the activation vectors or the tensor weight structures. This is now a spectral embedding, something completely different. And Howard tells us, hey, notice how such spectral embeddings are similar to the representation, see my video 1, from our models. And they have now a beautiful theorem, and they say here, this is in fact expected if you are a professor of mathematics at Harvard University, if our energy minimization hypothesis is true. Because if the representations that we have seen in video 1 from the model really minimize here the Dirichlet energy of the system and are non-degenerated, a mathematical detail, then the first two principal components of PCA will exactly produce the spectral embeddings of our system. Maybe you need a minute to understand this, and then in the second minute you say, can you give me a mathematical proof? Yes, in Annex B of the paper by Harvard University, you have here exactly this theorem now in perfect mathematical beauty and a proof. So if you want to have a nice weekend, you don't know what to do with your time, may I recommend here Annex B of the paper. If you're new to this, listen, if there are some simple ideas, you can go to ChatGPT for Omni or whatever you go, that doesn't really matter because those ideas are hundreds of years old, more or less. No? So a graph representation, what is a graph? What is a Laplacian? What is the Laplace matrix of a graph? The adjacency matrix, the degree matrix. Then you go to the eigenvalue and eigenvector, the decomposition here, and then you have here the embedding if you want. So this is for beginners, the easy explanation. How is this all with adjacency matrix, Laplace matrix, eigenvector, eigenvalue? How is this all connected if you do not want to read this 400 beautiful paper of Yale University? Great. Here I just want to show you, listen, this is really happening. This is really happening. Independent if you have a llama, 8 billion, a 1 billion, instructed, non-instructed, a small gamma 2, 2 billion, and 9 billion. Look at all the different layers. It is happening. The blue layers here, all this going down, the calculated Dirichlet energy that Harvard calculated for each and every single model is really minimizing itself. And then we have here really a minimum somewhere. And you see this is exactly where the learning, the in-context learning process starts. So if you want, again, we have here kind of fluctuations here about kind of a stable plateau at, let's say, 40%. And then when we have really the Dirichlet energy minimum, we have here the jump here in the performance over 80%. Let's see this here in a ring topology. See video 1. If we have here 100%, you see this beautiful here. The energy comes down, down, down. We have here then here kind of the minimum plateau here. And this is exactly where the real learning is happening now. And we have a saturation at close to 100%. So this mathematical model, this is really kind of describing here the behavior of this real system where we have here an LLM and we have in-context learning. I want to know how can we optimize our in-context learning? How can we understand the inner working? Do we have a model to calculate this? And to my knowledge, this is the first model that Harvard gives us here to calculate exactly that we see at what context length, with what modalities we can expect here from the modeling of the system where our in-context learning really takes place. And if we are somewhere left here, you know, you don't expect ICL to work at all. You can calculate this for each and every model. See maybe my next video. But let's come back to the main question. When, if you want to take away something simple, when does in-context structure, this in-context learning, the structures we provide with ICL, now really override the semantic prior of our LLM? Semantic prior, this means this is the model from Meta, this is the model from X or whatever. When you have your data that you want to insert, or maybe you want not just to add, but to alter a little bit of the reasoning connectome, when does it happen? This is also the reason why my last video was called How to Override Knowledge in an LLM. But now we have, if you want, a mathematical model, Harvard academic solution. But hey, we are interested here in a real solution we can implement immediately. So this is the sad truth. Harvard did here exactly this, the number of examples that is provided here when the in-context structure, in-context learning, overrides here the semantic prior, the pre-encoded knowledge of an LLM. So if you look at this in detail, this here demonstrates, we have the accuracy and the number of examples, X and Y axis, demonstrate the accuracy when given an in-context task that is now in a contradiction to what the LLM learned, contradiction to the semantic prior. We first observed that the model makes predictions that reflect the original semantic prior. So even if we have, 10 or 20 in-context learning examples, the LLM will stick here with its own pre-trained reasoning. Although it is going down. My goodness, you see from 70% accuracy, it's going down, 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 down. And here at, I don't know, whatever this is the number of examples here, we're really here, the linear fall comes down, and then we have also a different curve. But you know what is now interesting? When does the new in-context learning takes place? And this is here the blue line. So the accuracy here in pink drops very quickly as the model captures that the semantic rule that is learned is not being followed in these new ICL examples. So with more ICL examples given now in the prompt, we see here a slow decay of the remaining semantic security, and a transition to the model's behavior as it begins to make predictions that reflect now the newly defined ordering of our ring structure. This is not a blue line. The ring structure is an example from video 1. So you see between the behavior that the LLM still tries to hold on to the pre-trained value, originally from Meta. And when you provide here now examples in your prompt, when it catches up, you see, let's say 40% accuracy. You see that there's a valley of death, and this is where hallucination happen like hell, because the LLM doesn't know what to do. It's pre-trained knowledge. The more examples you provide, you see this pre-trained knowledge is wrong. I cannot apply it. And the LLM asks itself, so what knowledge should I apply? And if the new in-context learning is not there yet, what should the LLM do? It hallucinates. But there's another point. Look at how slowly we increase here with the number of examples, 600, and we start to come close to, let's say, 100% in the best case. So you see, this is now a behavior of in-context structure overriding here the semantic prior of an LLM that is showing us, my goodness, ICL to be really effective. Look, these are the number of examples you should provide. So it is not at all simple, easy, trivial to override the knowledge, the prior knowledge of your LLM fresh out of the Meta. And you know what? If you are a subscriber, by the way, which would be great, you remember that you have seen this curve before. And we see a similar behavior where I showed you in my video how the fine-tuning behaves exactly in the same case, but not with in-context learning, but really when we fine-tune the LLM. And now you see, what? You want to tell me that the in-context learning behavior with this valley of death and the fine-tuning, they behave similarly? Yeah. You know, if you really want to go to the AI, to the edge of research, look at this particular data. And can you explain this to me? That the energy minimization here with the in-context learning happens here in the dimension that really correspond to the in-context structure? Do you know what this means? Can you get? I can only imagine the implications of this. But yeah, this is beyond today's video. So let's come to an end. What is here the result? Harvard tells us, hey, these results I just showed you suggest now that we have here a context scaling in our in-context learning. Then this can unlock new capabilities of our LLM. And more broadly, this axis may have as yet been underdepreciated for improving here a large language model. Absolutely fascinating. So this might be a path to better LLMs, and maybe even a path to have a better in-context learning, that we know how to build in-context learning prompts, because we want that this scaling is happening and unlocking new capabilities. Yeah. Now, at the end, if you are really one or two of my subscribers who come to the end and still are here with me, I want to give you some personal reflection and insights. At this point in time, I feel that if we do a pre-training of an LLM, this pre-training dataset, this pre-training knowledge that we imprint on a large language model, on a transformer model, is the dominant factor. Because if we then add here fine-tuning, you know, this very tiny little, if you want, sphere of fine-tuning knowledge, fine-tuning information, fine-tuning data, new data, what we really modify is just a minor, really tiny little sphere. And you think, but this is more or less true also if you want to go with in-context learning. I just showed you when we have an override of the knowledge given the semantic prior. So in-context learning, although we thought it is so easy, in reality, if you really examine it, it is not easy at all. And there are a lot of second phase order transmission. And you know what we do? I have the feeling that we do not care about the optimization of this system. You know what we do? We build complexities that are outside of the core of the LLM methodology and functions. We build RAG systems that have a complexity with an indexer, a re-indexer. Then we have here the main retriever. We have a pre-retriever. We have a re-retriever. We have 3 agents, I showed you in my last video, to optimize the RAG system, because the learning is not really happening. But I have a feeling we don't touch here the real core of the problem. To me, currently in this time, it seems we are just building construct outside, and we try to get a grip, to improve the accuracy, to get a better model, but we are just building more and more complexity outside of the core of the LLM. And you know, this reminds me a little bit, if you think about the current research in quantum error corrections, I also have a feeling there, we are not really tackling here the main issue of the system. So outside, we build complexities that are just amazing, you know, but maybe in AI research, this is not the path forward. But okay, let's say for this video, this is end of part 2. Part 3 is in the making if I get some positive, 1 or 2 likes of this video. Otherwise, it will get even more complicated. But what we have achieved today, we have looked at a new mathematical model. We understand that the model now, our LLM, internally with this hypothesis of Harvard University, runs an energy minimization process. We can describe here the features of the process. And this energy minimization is now in search of a correct structural representation of the data. And this is mind-boggling. Can you imagine this? We have now a connex between a structural data representation, a neural network architecture, a transformer architecture, and what we do on all of this complexity, we run an energy minimization process, and this gives us the right results. I find it fascinating. So if you're a little bit into mathematics or a little bit more into theoretical physics, you're gonna enjoy the future of AI. And today we only looked at in-context learning. There's a lot of happening currently at the pre-training of LLMs that I would like to show you. Maybe this is even more important, because it turns out we are just building complexities that are not really tackling here the real problem of AI research. So if you're interested, maybe you think you would like to subscribe, and it would be great to see you in my next video.